Welcome back. And now I've just got a few things I want to go through in order to finish up these complexity notes. I'm going to talk about C to Verilog with a lot of caveats, and then talk a little bit about power consumption in modern designs, which is something we'll return to in more detail in a later module. So I'm about to present how to, at least conceptually, translate from an algorithmic C representation to Verilog, emphasizing the way not to do it is to put a few always at statements around and hope for the best. However, this process I'm describing here kind of doesn't work very well because it's going to be done piece by piece through the code and doesn't necessarily lead to an overall efficient design. In fact, it will lead to a very inefficient design. However, if you get stuck, this at least shows you ways to think about things and does emphasize that you don't go from algorithmic intent to C to a hardware design simply through a few coding tricks. So we'll start off with this simple example here. We have this code, an if statement with a couple of selectors. Now, since the if statement in the algorithmic code is specifying a sequence of operations, this really means that you've got a finite state machine producing a control signal defining a sequence. And this control signal is controlling some hardware that includes this multiplexer and includes logic producing a zero flag in order to do it. So the if statement is becoming a branch in a finite state machine, and the assignment is becoming structure in the data path. Again, this is a simple generality. It isn't necessarily the most efficient way to map algorithmic intent onto hardware. Also, an illustrator happens with a for loop. In C, you might have a for loop like this. Again, here what we're doing is accumulating a series of values onto B. Again, if we just put this in an always at plus block, we'd actually be building 8 adders, which wouldn't be very efficient and would lead to a bloated and slow design. So in hardware, what this becomes is the for loop becomes a controller, in this case a counter, a linear sequence, counting 8 cycles, possibly within the context of a larger finite state machine. And the structure on the right hand side becomes a data path element, in this case an accumulator that's initialized to B on the 0th cycle. This again is illustrating that a for loop in C does not become a for loop in Verilog, it becomes a counter in Verilog. So again, I'm specifying what is data path and what is control here. The control statement in C is becoming control logic in the digital logic design. Next, I just want to discuss a little bit about minimizing power consumption. The reason I'm doing this now is because you're going to start thinking about doing design. At this stage in the class, you'll be facing the project. And though I will return later to talk quite a bit about power consumption, I want to just introduce you to the basic concept. And that is, in digital CMOS, the way to compute power consumption is roughly proportional to adding over all the logic nodes in the design, including the ones internal to blocks, the sum of all the logic transitions. Each logic transition consumes power. So 0, 1, 0 transition on one logic node consumes 1 energy of power. 2 of those transitions on one logic node produce 2 units of power. One logic transition on 2 separate nodes also consumes 2 units of energy. Each of these is a specific amount of energy. Taken over per unit time, it becomes power. Again, we'll return to this in a later set of notes. One thing I particularly want to point out is that complex logic units, such as multipliers, have a lot of internal nodes and thus consume a lot of energy per operation, Thus you have to be very careful to make sure that that energy is doing something useful and is not being wasted within the multiplier. And I'll illustrate this in a moment. So here's a couple of examples. On the top we have two comparators that we've looked at before. The left-hand one is the simple, what you get from straightforward coding. The right-hand one is a pipeline version. The right-hand one is faster, but which is more energy efficient? I think you've recognized it's the left-hand one because it has fewer logic gates and thus fewer toggles per comparison performed. Okay, let's look at another example. Let's say we have a multiplier, but we're only using the result of that multiplier every now and again as controlled by this select line B. The question is, which is more energy efficient, the logic structure on the left or the logic structure on the right? Well, it turns out the logic structure on the right is more efficient, because by using B to prevent the inputs from changing, we're preventing internal toggling when we don't want to use the multiplier, and that is what is consuming the energy. On the other hand, the structure on the left-hand side, whenever the inputs change, even if B is off, all the internal modes are going to transition because of those changing inputs, producing a lot of energy. And if B is off, we actually didn't want that computation. We're not using it. So the energy in the multiplier is wasted if B is not selecting the multiplier. On the right hand side, we've done is added a couple of flip registers to the input and multiplier. The idea is to use the registered value from the last useful computation, and if B is saying we don't want a new computation, present that last set of inputs to the multiplier and keep them frozen on those inputs to the multiplier. Thus the inputs are not changing while B is selecting off, and thus the internal nodes of the multiplier are not changing, which would consume energy if they did. There I've been dealing with energy and power at the module level. I do want to also remind you that some big consumers of power in design, particularly long distance wires, and in particular off-chip wires, are very consuming power. In fact, more so than the multiplier example I was just giving. So that brings us to the end of this particular submodule and the end of this complexity module overall. For this submodule, I remind you, you can translate C to Verilog, but I suggest only doing this if you're stuck in a design as to how to proceed and just need to start thinking through how to approach it. In each case, the control logic in C becomes control logic in the RTL, and what's being controlled becomes data path in the RTL. And if you want to think about minimizing power consumption, generally think about minimizing the total number of node toggles across all the nodes, and by that I mean all the outputs of all the individual logic gates within a design. Minimize that total number of node toggles to complete a computational task. So that brings us to the end of this module. Again, there's been a quiz associated with each submodule, including this one, leading to a full quiz and a homework. I hope you got a lot out of this module and can start at least you thinking about how to approach more complex designs with some methodology and rigor. Thank you very much.